The recording is in progress. I wanted to say that I don't, let me stop synchronization. Options. I don't need you to synchronize. Okay, it's not. It's just doing some weird stuff. I always like to say that I don't like wasting people's time. So if you already came here, probably you had like lots of other things to do, other exams and everything. And I don't like wasting my own time either. So if we're already here, let's make sure it's a good review. That's kind of my point. So I'm known for giving really good exam reviews, because let's not have like just a check mark that we attended the review. Let's have a good one. So let's do it. I will first review a little bit of differentiation, and I will do all of them right away. Differentiation. That will help you with all of those exam problems about derivatives and the exam about derivatives. So in general, derivatives will be everywhere. Exam 2, 3, mastery exam, final exam, calculus 2, 1, 2, 3, final exam, and calculus 3, 1, 2, 3, and final exam. Differentiation is literally a heart of math, so you have to be good at this. We're not supposed to pass people from this class if they don't know differentiation. Right away, if you're bad with memory, do it this way. Remember, you're supposed to remember derivatives of cosine and sine right away. Sine behaves like a normal person, like a normal function. I'll make a joke about it because it's easy to remember. Sine is a normal dude. It gives you cosine. At 0, it is 0. So it's like a very classical dude. It starts from 0. Cosine is always weird. And it gives you minus sign when you differentiate it. At 0, it is not 0. And that helps you to calculate and remember. Sine goes first, and cosine is doing something weird. But they alternate. When you differentiate or integrate, we'll be learning integration soon, they give each other. Now, tangent. So, that's what I wanted to say. If you're bad with memory, just like me, I always had bad memory for formulas and dates. This is what you do. You review the formulas before the exam. And then you're not allowed to have any formula sheets on a test. So when the exam starts, write down whatever I'm doing very fast during the exam on a scratch paper. That is allowed, right? You can write down your thoughts. So that's what I would always do. Tangent x likes secant so much that it gives you secant square when you differentiate it. But secant likes itself. So when you differentiate secant, it gives you secant. And then tangent that likes secant. That's a funny joke, helps people memorize formulas. Those are trigs, not enough. Later on, we tortured you with arctangent, arcsine, arccosine. So we also have more. What is derivative of arctangent or tangent minus 1? It's the same as arctangent for you to know. Prime. That is 1 over, and this is how I will show you. Let's call the piece inside U. The derivative of arctangent is 1 over 1 plus input squared. So whatever that thing is, you multiply by that thing. Whatever that thing is, you square the thing in the denominator. So that's the formula. The other two, secant, sine and secant, have square roots. The only problem is to remember which one starts with 1 minus. Do you remember which one starts with 1 minus? Secant of u, and that is arcsecant, and arcsine, or inverse sine of u. Both of them are 1 over the square root. I don't like this. But then one is 1 minus input squared, and another one is input squared 1 minus 1. Which one do you know? Let me check if any. Do you know which one which one is 1 minus stuff? That's kind of the only difference, actually. So that's your memory for you. You need to learn this for the test. I remember that sine is a normal. So it starts with 1 minus. u squared, u. And then secant is so proud of itself that input goes first. And this kind of joke doesn't make sense here, but whatever. So this is important. Those are trigonometric functions. Now, we learned log and exponential functions. Those are not too bad. E to the x gives you e to the x. However, chain rule is getting involved almost all the time. So if you have e to the u, then you copy and multiply by the derivative of the exponent. That is the idea here. That's chain rule. In general, that's not a new formula. So usually we teach the original formula. E to the x prime gives you e to the x. A to the x, what if it's not e? It will be copy multiplied by the ln of a. I did not put on the test any weird derivative with different bases, a, like 5 to the x and stuff. Same with log. To be honest, the second formula, everyone should know it, but many people just don't, and they still become PhDs and whatever. Log, this is a really cool one. I really like the derivative of log because it's 1 over everything inside. Like so, 1 over everything inside. But if that thing inside is a function, then times u prime. In general, it's always like that, times u prime, times u prime, times u prime. If there is a function inside of the function, you first differentiate it the way you know, and then you do times derivative of that function. And also there was like a formula for log base a, let's do x. You do 1 over x, so 1 over everything inside, but also 1 over ln of a. ln of a is like fixing the situation with the different base. We don't like to have not e, so to fix it, we multiply or divide by ln of that base. And it actually works with e as well. It's just derivative of e to the x is e to the x times ln e, but ln e is 1. That's why we don't write it down. So this classic stuff, everything else comes from that. We're gonna learn more. Actually, I think that's all classical derivatives. There are also cosecant and stuff. Nah, nobody tests that. That's actually very cruel to test these derivatives. A, nobody remembers them. And B, you can just jump from cosecant to sine and cosine, like cosecant and secant. So why do you even care that much? Secant is very popular in America, so they try to push that one, mostly for engineers, because secant does show up in physics a lot. So I think because of that one. Okay, let's do it. So this is your formula table, which you unfortunately cannot have on the test. And we're going to start with some classical examples of product rule and quotient rule. Product rule and quotient rule. My notation is short. I like being fast. So u times v prime is u prime v plus u v prime. Derivative, not derivative, not derivative, derivative. That's how I teach it. It doesn't matter how you remember it. Just make sure you remember. U over v, that's a quotient, is always start with squaring the denominator, because then you will not forget to do it later. Many people forget to do it later. So I usually start with it. And then differentiate the top first. Then it will help you with the order. U prime v minus u v prime. Of course, some things can be changed, like this order can be changed, but some things cannot be changed. You cannot change these two pairs because of the negative sign. That's why I teach start with differentiating the top numerator. Then you're right. Then you will not make a mistake. But it's not like it's required. So it's fine. It is a formula, it is a procedure. So just make sure you know how to do it. Examples. And I have lots of examples. Quotient rule. I already have lots of examples recorded, but we will practice something like this. find f prime. That's going to be literally like half of the exam is asking you to find a derivative. Because again, like I told you, we're not supposed to pass you if you cannot take derivatives, all kind of derivatives. So that's basically why all the tests have derivatives. Find f prime 1. Okay, solution. You notice that it is a product of functions. Either you distribute and you have 4x and sine and 4x and cosine, or you just keep it factored. I will keep it factored. So this is u and this is v, 2 factors. The formula says f prime. Derivative of u, 4x gives you 4. Copy, let me write down. Copy the other one. So I'm copying sine plus cosine. Okay, sine plus cosine. Copy. Plus, either you take derivative or copy the first one. Here, order doesn't matter in this case. It says copy u. So I will copy 4x. Copy. Times derivative of sine x plus cosine x. And you remember, sine is normal, dude. So derivative of sine is cosine. But cosine is a troublemaker. So derivative of cosine is minus sine. Like so. So derivative, non-derivative, non-derivative, derivative. And you can switch to order. Just make sure you have those pairs. Okay, that's it. On the test, I recommend you not to simplify anything. Just plug it into the solution. And if we ask you to plug some number like 3 pi over 2, and oh my goodness, you forgot what the sine of 3 pi over 2, that is fine. I don't know why everyone always so pushy about the circle. Yes, it's important to know at least the common angles. But on the test, people are freaking out. So I don't see what's the big deal. So don't just type it in as it is. Sine of 3 pi over 2. Just type it like this, and I checked, exam program will accept it. So in none of the problems says you have to simplify. I made sure of that. There was one problem and I deleted it. It says simplify, like whatever. The life is too short for too many steps on the test. So that's my comment here. What if there's a function for the log? Yeah, I will show you the log in a second. So that's the answer. So I would say type this. Don't have to, if you're freaking out of what is sine of 3 pi over 2, whatever, just type it in. This is good. Now, let's do quotient rule. 2. So we keep finding derivatives. I don't have to say find f prime. That's kind of common sense. It's already too popular. So we'll do some logarithmic function and quotient rule to make it complicated, basically. So it will be ln x, and then we'll have 3e to the x plus cosine x, like so. And I just put prime. So I wanted to also comment on this thing. It's surprisingly, I mean, it's fine. Not everyone, I think, understands this idea. I'll go back in a second. Derivative of a constant is 0 if it's standing by itself isolated. But if a constant is glued to a function, then it's not 0 anymore. Derivative of x is 1. So derivative of ax is a times 1, or just a. That is because if it's standing by itself, if it's isolated, just standing by itself, it's a constant. And then derivative asks the question, how fast something is changing. Well, how fast constant is changing? Constant is not changing. That's what's called constant. So the speed of constant is 0. But if it's multiplied by a function, then it's rate. Moreover, it's rate of change. That's why no wonder when you differentiate that, it shows up because it's part of the rate. Example, for example, like 157, so differentiate that, plus 3.5 x squared minus e squared plus e to the x. Probably can just use it as example. So let me show it to you here. Yeah, we're gonna do quotient rule in a second. What my point is, check this out. E to the x prime. This is example 3. Derivative of 157 is 0. Derivative of 3.5x squared is not 0. It's 3.5 times 2x. Derivative of e squared is 0 because e is a constant, but derivative of e to the x is e to the x. So you have to be good at understanding the difference here. Check this out. Power rule, we use power rule for x squared, but e to the x is not polynomial, that's exponential function. So those two different rules. This is called power rule, which is a to the x. Yeah. X to the a, x to the n. X to the n prime is n, x to the n minus 1. That's power rule. But for the exponential, we use exponential rule. What a unique name for the exponential function, which is e to the x gives you e to the x. So you need to be good at this. And this is constant. But this is also constant. 3.5 is also constant, but it's glued to a function. If constant is glued to a function, so now it's a rate, so it stays. That's my idea. Okay, let's perform a quotient rule. The formula is u over v, square denominator. So I will do that right away. And don't touch it. Just type it like that. Just keep it as ln x. Don't forget parentheses around, squared. Remember, ln x squared is not the same thing as ln x squared. One squares the whole thing, so it's ln x times ln x, while the other one squares the input ln x times x. So make sure parentheses matter, basically. Yeah, quite often. Now, formula says, here's the formula on the right. Differentiate the top first. That's my recommendation. You don't have to, but it's my recommendation and it's good. Derivative of 3e to the x is 3e to the x. Derivative of cosine is minus sine x. Okay, that is u prime. U prime times copy v. I'm copying ln x. Don't forget minus. Minus is part of the formula. It came from derivation of this formula. So minus is crucial. Now, copy the numerator. Copy again the numerator. Not again, we never copied yet. 3e to the x plus cosine x. And now times derivative of the denominator. And we know derivative of log is 1 over input. That's it. Don't simplify this for the test. Just plug it, just type it in carefully. If we ask you to plug something, plug in, type it in. So that is the answer. Quotient rule. Quotient rule. Now I'm going to go to chain rule because that's the troublemaker. So that is the answer. Product rule and quotient rule. Let me check chat quickly. Come on, it was supposed to be a beautiful table. Yeah. Let me check. Yes, of course, we're going to do implicit differentiation and everything. So we got the constants. Let's do chain rule. That's the one people stuck a lot, usually. But you know, you get used to it with time, for sure. I do promise you that. You get used to it. For example, what is derivative of sine 3x squared plus 5? Okay, chain rule. I teach it using Russian dolls, and I actually do have them. I bring them to class. And I show students that it's basically a nest of functions or nesting functions. function. That's a Russian doll. If you don't know what Russian doll is, basically a doll. It's a wooden doll with more dolls inside. And then I'm gonna sneeze. So here it is. There is an outside function first. Your job is to find out which function is outside and differentiate that function first. Well, I do see that it is sign of stuff. Sign is first because sign is very outside. The thing is, you don't see the next layer. Let me put it in a different color. And then there's a function on the inside, and maybe there's more functions and more functions. So Russian dolls are nested dolls. You don't see them until you open the first one. So you have to open it, and then you see, oh, there's 3x squared plus 5 inside. This helps you to remember how to differentiate. Since you don't see it, you don't touch the inside part. You have to copy it until you finish differentiating the outside part first. So I see that sine is the first derivative, is the function outside. Derivative of sine is cosine. And I cannot touch the part inside because that's how chain rule works. Copy the part inside first. It's like in computer game. You cannot get to the next level until you finish the previous level. But I like it explaining through the Russian doll. Now, when I put times, this is when chain rule says, oh, don't stop. You never differentiated the function inside. Now you can open it and see what's inside. So now I'm opening and I see one more Russian doll inside. And that Russian doll has a function 3x squared plus 5. So now I do times derivative of the function inside. I'll be saying this phrase a lot. Derivative of the function inside. Can you do this on a test? So outside function, it's called otter, right? 1t or 2t. Otter. One is the animal, the other one is outside. Otter. Otter. Hey. And one is inner. You got it. So you first find the outside one. Differentiate it. That is the answer. Don't do anything weird about this. Don't simplify. There's nothing to simplify in this case. Don't overthink this. Type this in. I make sure that you can just do that. More. How about arctangent? Arctangent of, let's do 7x. Look at this. Arctangent, formula for arctangent, let's remind you. Derivative of arctangent. I like to write down 10 minus 1 because it's faster. Arctan of u prime is 1 over 1 plus u squared. Whatever is inside, you're squaring it. Then times u prime, that's chain rule. So you multiply by the derivative of the function inside. So first I'm understanding that 7x is the part inside. So I do 1 over 1 plus, 1 over 1 plus 7x squared. Don't even have to simplify this. Just leave it as 7x squared. Times the derivative of the function inside, which is times 7. So that is chain rule times 7. See? And you can put it in the numerator, of course, if you want. And you can sometimes collect the terms. Number 4. There's a question. Chain rule with log is coming. We do not do a minus for the exponent. Since there was no exponent originally. Minus 6x. Yes, there was no exponent originally. 6x. Yeah, and there's a good comment there. So there was no exponent. This is inside of sine. I would say sine, if you remember, is a function of the angle. So that thing inside is the angle. Something like pi over 2. It's just written as 3x squared plus 5, but maybe it's pi over 2. So you differentiate the function outside, that gives you cosine. Copy the inner part because you have no rights to touch it yet. Times, now forget about cosine and sine and look inside. You look inside and you see 3x squared plus 5. And you do, oh, the derivative of that is 6x. That's how I see it. Let me know if that doesn't make sense. I can have more ideas how to explain. I'm very creative when it comes to explaining things. So, log, very interesting also. Check it out. What is derivative of log of 7x? This is so funny. Look at this. Look at this. So log says 1 over the input. Derivative of log is 1 over input. Then you notice that the input is also a function. So you do times derivative of that input. That's 7. So it simplifies to be 1 over x. How cool is that? You don't have to simplify, but it's just funny that it simplifies this way. However, sometimes it's more complicated than that. So, for example, we will have a square root of ln of 7x squared minus 3. How about that? So there's going to be chain rule twice. You first identify what is the function, the very, very outside. Let me make a sketch for you. So the first big Russian doll is a square root. So you see a square root function first. And square root has everything inside of it. So I first differentiate the square root without touching log and the polynomial inside. I will just copy it. I can actually even keep showing you. So the first is a square root. That's power rule. We will do that in a second. Then a next level inside of the square root. Also, square root is a function of 1/2. It's raised to the 1/2. Inside of it is log, ln. And then inside of log is a polynomial, which is 7x squared minus 3. That's how it looks. So let's do it. First of all, you should review how to take the derivative of square roots. Students usually struggle with this, so I'll review it here. Square root of x prime is, before taking the derivative, maybe rewrite it as x to the 1/2. In the future, you will stop doing that because you'll be very good at this. But at the beginning, it's helpful to rewrite it as 1/2 power. Then power rule says 1/2 goes down, multiplied by 1/2. X decreased by 1. 1/2 minus 1 is negative 1/2. And you can keep this as the answer. Many students memorize that it is 1 over 2 squared of x, but you don't have to do that. We are playing with exponents basically here. So both answers are good. Let me review this very quickly. Now, probably, if you took calculus a long time ago, you're probably freaking out about this idea. So let me review that really fast. That's totally okay. Nobody remembers this unless you're actually using it. X raised to the m over n is x. This is how I teach it. Whoever was at the top, which is numerator, will stay at the top. Whoever was at the bottom will go to the root. So usually people write down like so. M was at the top, so it stays at the top. N was at the bottom, so it goes down to the root. That means, and of course, the square root of x is x to the 1/2. That's one of the special notation. That's a square root. Other are not called square root. So, for example, if you see x cube and the 5th root, how to rewrite it? You can write down like this. 3 was at the top, so it goes to the top. 5 was at the root parts, kind of at the bottom. So I'll put it at the bottom like that. So here you go. Now you can differentiate all kind of functions. If you rewrite them as a fraction, this is just power rule. 3/5 goes down. Well, actually, I can do that. Let's see. The first thing is a formula. Others are just examples. Those are powers or exponents, powers rules. So In that case, if you want to differentiate fifth root x cubed, you first rewrite it. So you see I keep parentheses. That means I did not differentiate it. I'm just rewriting whatever is inside of the parentheses as 3/5. Then power rule of differentiation says 3/5 goes down, which means you multiply by x. 3/5 minus 1. Do you know how to do that fast? 3/5 minus 1. 1 can be anything you want. So it's 5/5, 4/4, 17/17. In this case, I want 5/5 to create common denominator. So that's how fast you think about it. 3/5 minus 5/5. That's minus 2/5. And leave it like this. Nobody wants you to rewrite it. Some teachers do, and it's very rude in my point of view. Nobody cares to rewrite it with the positive exponents. We want to know that you can differentiate. So that's actually the most important. Okay, so going back to the square root, that's why I was showing all of this, because I plan to, I can just keep it without prime first. I plan to rewrite it first as ln 7x squared minus 3, huge parentheses, raised to the 1/2, because that's what square root is. So now, this is f. So now f prime will be 1/2 goes down. Let me keep it in green. Actually, what is someone here is color coded? Well, you should let me know if you color code it. Let me know as soon as possible, so I don't use whatever color you don't like. Color blinded. That's what I wanted to see. Now 1/2 goes down. Copy everything inside, because you remember you cannot reach it yet. This one is hidden from you. The inside Russian doll is hidden. You have to first finish with the outside differentiation. So I'm gonna copy whatever is inside, no matter how crazy it is, and then change the exponent. 1/2 becomes minus 1/2, because 1/2 minus 1, that's power rule. Copy the whole thing, ln 7x squared minus 3. Then times, and I will change the color. Chain rule starts. Chain rule says, well, whatever is inside is also a function. And I only see log for now. I don't see what's inside of the log, because that's inner part. So I know derivative of log of is 1 over stuff. So I will do 1 over 7x squared minus 3. Copy that, I'm copying this. Then I do times. Chain rule happens again, and I'm going to change the color to blue. Now chain rule says, oh, I also see 7x squared minus 3. Let's differentiate that. Derivative of that is 14x, and I'm done. Yeah, you can simplify that, rearrange things. 14 over 2 is 7. But like, why would you? Just type this carefully and move on like so. That's why chain rule twice. Yeah, with log and stuff like that. Let's see. Let's do this example and then move on to harder stuff like implicit differentiation. What is derivative of 2x squared arctangent of 8x squared prime? So you write it down, you look at it, you get scared, and then you start thinking, seems like there are too many functions multiplied, so that's probably going to be product rule. Product rule, let me call this function to be u and arctangent to be v. So it's u times v rule. U times me tell me differentiate the first function, that's going to be 6x. Copy the other factor, arctangent 8x squared, and you copy. Now, plus, copy the first function, 2x squared. This is basically derivative, non-derivative, non-derivative, derivative, in any order you like. And now derivative of arctangent. Arctangent says 1 over 1 plus whatever was there squared. 8x squared, everything squared. And you don't have to simplify that, just keep it like that. But then chain rule says, wait a second, there's a function inside. So you cannot stop here. You do times, and that times.
I think you made a mistake. I think it should be 4x.
4x. Oh, very good catch. You're right. Why did I put 6? Good job. 4x. Good one. You see, people paying attention. Good job. Chain rule, let me finish chain rule. Chain rule says times the derivative of 8x squared, which is 16x. Very good. See, very satisfying when people paying attention. I always say I did it on purpose, and usually that's a lie. And yeah, you can simplify this, but yeah. So copy, and then chain rule is performed. Good. Let's do implicit differentiation. Oh, my computer is overheating. So let me turn off extra stuff. So yes, I was showing if people are late about the channel. All of this is here. I want to turn off browsers because it's too heavy for the computer. I wanted to mention that I did lots of stuff. We're going to do implicit differentiation. Right now it's here. Logarithmic differentiation, everything. My point is, and all derivatives are here. I call it mastering differentiation list. My point is, I can show you thousands of examples like this, but that will not make you better at differentiating. You have to go and do it yourself. That's my point. It's like with push-ups. I cannot do hundreds of push-ups and then claim you're good at this. You have to watch how to do it and then do it yourself properly. So that with derivatives, there's no other option. You have to go and just do it 100 times, 50 times. Everyone have their own amount to be good at it. So don't get discouraged, just do it. Do it. Implicit differentiation, let's do this one. That's 2.6. Find the slope of a tangent line. Find slope, that's fine. Find the slope of the tangent line. To the curve 5xy to the 5 plus 3xy equals 24. At slope is always at the point. So this is how I teach in Calculus 1 classes. First of all, we will be asking to find the slope for like 3 semesters or more. Calculus 1, 2, and 3. In third one, we're going to do it in upper dimensions, 3 dimensions, 4 dimensions, and so on. Because it's extremely important idea. So the moment you see slope, the moment you see the word tangent, that's derivative. That's literally synonym. Derivative, it's like a keyword. I would say, like, you can make a note somewhere. The keyword is derivative, differentiation. If you see slope, slope is derivative at the moment. If you see tangent, yeah, they want you to find derivative. If you see the word instantaneous rate of change, instantaneous rate of change, yeah, that's also derivative. In business classes, they have marginal cost function, marginal profit function, so on. That's also derivative. And other things, velocity, right? Like if you see velocity speed, which are not the same thing, by the way. Then one is always positive and the other one is not. That's also derivative. So the moment you see some of these words, you know what to do. At least you know how to start. They want you to differentiate. The problem is, right before that, we did so many examples when f was given explicitly. F equals, or y equals, right? Y equals, blah, blah, blah. Find y prime. What if it's not given explicitly? What if it's hidden all over the place? And it's going to be a headache to solve for y, or sometimes it's even impossible. That's called, it's given implicitly. So instead of solving for y, you just differentiate everything right away, like through a bomb and it just blows up everything. So that's called implicit differentiation. We will not be looking for y, but we are asked to find dy dx. So how are we going to do it? Implicitly. Differentiate everything you see, keeping in mind 2 ideas. This is how I teach it. When you differentiate x or anything about x, that will be 1. X is the independent variable. It's the input. When you differentiate the input, it treats classically the way we just learned. However, whatever is output that depends on input, that's what's called dependent function variable. Derivative of y will be written as dy over dx like so. So it's not 1 anymore. It's 1 times dy over dx by chain rule, actually. So input versus output. Output is a complicated guy and input is a simple case. Keeping this in mind, let's perform implicit differentiation. Implicit, because we can't do it explicitly. Differentiation. Let's do it. 5x y to the 5 is a product rule. So I will differentiate it using product rule. Derivative of 5x, I'm keeping in mind, x is a normal dude. So 5x gives you 5. We know that. Copy y to the 5. Copy y to the 5. I can do that. That's not hard. Plus, copy 5x. I can do that too. That's not too bad. And now the hard part starts now. Differentiate y to the 5. You first perform normal differentiation rule. In this case, it's power rule. 5 goes down, y to the 4. Then you want to stop. But then it reminds you, wait a second, y is not a simple dude. Y is the output. So actually chain rule happens over here. This is where chain rule shows up. Chain rule says differentiate the function y, and that's why you write down dy over dx, or y prime, if you want. Chain rule says don't forget to multiply by the derivative of y. Because we don't know derivative of y, we cannot write down the explicit shape of it, like sine or cosine. That's why for now we just call it dy over dx. That was just a result of the first part. Plus, the second part is also a product rule. 3x and y. Now let me put in a different color. Let's be faster. Derivative of 3x is 3 multiplied by copy y, copy, plus copy 3x. Derivative of y is 1 times dy over dx. Yeah. So that's the second part. The second part. Equals to 24. Tell me, where is the mistake? I always make this mistake. There should be people remember to do this differentiation. It should be 0. Exactly. Don't forget to differentiate the right-hand side. People get happy that they finished with left-hand side because it was hard, and then they keep 24, and then everything is wrong, and it's just upsetting. So right-hand side is derivative of 24, which is 0. Okay, the step 1, implicit differentiation has steps. I teach with steps, so when people freak out on the test, they can still do steps, and it looks good. Step 1, differentiate everything you see, keeping in mind the rule I mentioned before. Step 2, locate dy over dx. I like color coding, so I will do that. Here it is, and here it is. Move dy over dx to the left-hand side with all the stuff attached to it. 5y to the 4 dy over dx is already on the left-hand side, but it's also multiplied by 5x. So let me just put it in front. I could simplify, I guess. 5 times 5 is 25x, y to the 4 dy over dx. Plus, what other thing is there? So this guy, the whole term will stay on the left-hand side, and this will stay. Everything else is garbage. Move it to brain. Like that, just, we don't care about that. So the second part is 3x dy over dx equals, and you move everything to the right. So it's going to be 0 minus 5y squared minus 3y, like so. So step 2, we're relocating things. We want to isolate dy over dx on the left-hand side. That's the final goal. To do that, you perform 2 steps. Locate terms with dy over dx, move them to the left, everything else to the right. Step 3, factor out dy over dx. You want to have the picture like this.
For step 2, should the 5y be to the 5th power?
Oh, thank you. See, good catch. 5 is here. 5 is here. Good job. Okay, good. Rewind. Okay, good job, people paying attention. That's good. So factoring out, again, I will color code. So this guy and this guy, I will factor it out. And then what I will be inside of the brackets will be the leftovers. 25xy to the 4 plus 3x equals right-hand side. RHS is notation for right-hand side. Like so. I mean, okay, let me write it down. But to be honest, we need it at the very end, so that's why it's not very interesting to keep writing it. Minus 5y to the 5 minus 3y. Finally, the answer follows right now. dy where dx equals right-hand side over those brackets, and that is the answer. So dy over dx is right-hand side is minus, I said minus 5y to the 5 minus 3y over 25xy to the 4 plus 3x. Put it in the box. Type it in as the answer for dy over dx. And then if we ask you to plug the point, you plug the point. I'll do it in a second. Now, very interesting. Before, we did not have answers with x and y at the same time. Here we have y. So interesting, the derivative now depends on input and output. That is because we did not know what y equals to. Like at the very beginning, we don't have this information. That's why if we knew, we would not even perform implicit differentiation in the first place. But since we didn't, then, you know, it just there is a variable. And now they ask you to find a slope. They gave you the point, so you plug in the point. Plug, and the point was 3 in 1. Plug 3 in 1. You can always sign that this is x, comma, y, right? So that's visually will help you not to mess up. I highly recommend to take a pencil and sign it. And then visually it will help you. And I'll just plug it right away. And I'll give you some kind of number. Minus 5, 1 to the 5, minus 3 times 1, 25 times 3 times 1 to the 4, plus 3 times 1 equals, I do have the answer, minus 2 or 21. That is a slope of a tangent line. If you did not multiply to get 25 in step 2, would the answer be wrong?
How did you get?
No, the answer will be the same. You can keep it as 5 times 5.
Excuse me, how did you get 3 times 1 when the it says 3 times x and x
3
is
times x. Oh, you're right. X is
yes, so
3. Fixed. Okay. Good catch. See? Good job, people paying attention. Good catch. Very good. So practice that. Yeah. There's one more I can do later if I have time. Implicit differentiation, again, you just need to keep practicing. So the other one is with trigs. I would highly recommend you to practice that one, number 10. Make sure you do this one by yourself. 5 sine x plus 4 cosine y minus 4 sine x cosine y plus x equals 7 pi. I think I have video on this because it looks very familiar. So practice that. Also product rule, but now with trigonometric functions and chain rule. What is derivative of cosine y? Derivative of cosine y will be minus sine y parentheses times, times dy over dx. So you need to practice that. You need to be good at this. Unfortunately, even one mistake basically ruins the whole problem. So still overheating. Okay. Let me decrease the brightness. Nice. So now we can move on to more differentiation. Let's do logarithmic differentiation. That thing is also there on the exam, and actually it's there twice. It's there at the very last topic, which you're doing right now, which is logarithmic differentiation for the L'Hopital rule and stuff, but also improper integrals and stuff. Oh, no, that's not improper integrals. I'll show you in a second. And right now, it's called logarithmic differentiation. Logarithmic differentiation. Very interesting. I like to explain this idea. So we have x to the a. That is the input raised to a number. Number, I mean a constant, right? Number. So that is a polynomial. While, or do versus, let's do versus. Vs. We have a to the x. That is a constant raised to the input. That's called exponential function. Very interesting, right? Versus, and now we learned a new one. There's an input to the input. And not necessarily x to the x. It can be x to the sine x or sine x to the cosine x. That is input to the input. This function doesn't have a name. You can actually check Wikipedia about that. It doesn't have a name, but it's a very fast function. Usually exponential function is the fastest. Well, actually factorial function is faster. X to the x, input to the input is the fastest function. Fast. Because input is already growing and exponent is growing and input is raised to that exponent, so you can imagine. So we know how to deal with polynomials. We use power rule. Power rule. So it's going to be ax a minus 1 when you find a derivative, right? A to the x, we use exponential rule. We just did that. That's going to be copy times ln of a. X to the x, there's no such a rule here. There's no specific formula for it. You have to use logarithmic differentiation. Logarithmic differentiation is not a formula, it's a process. So that's why I don't want to put it in the same line. Logarithmic differentiation says, example, y equals x raised to the 6x. You recognize it is not polynomial and it's not exponential function. Thus, you have to use this input to the input strategy of using logarithm to both sides first. You apply natural logarithm to left-hand side and right-hand side. And you end up having ln y equals ln, open parentheses, x 6 to the x. Why you're doing this? Because logarithm function is the only function that is super awesome. It's actually, if you Google top 10 or top 20 most powerful formulas in the human history, of course, you will see gravitation forces there, even black hole formula, of course, Newton, blah, blah, blah. But then logarithmic function is there. Exactly for that one important reason. It takes the exponent and puts it down. It's like, it's really cool. Nobody else does it. Logarithm function is used quite often to slow down processes. So ln of m raised to the n takes that n and puts it down. And now you multiply by, instead of raising to it. So we used to have exponent. Now we have product. And product is much slower than the exponent. So when computers were just created, logarithmic functions were used a lot to save space and computations, and they still do actually. And in science, logarithmic functions are also used to slow down fast processes and make calculations when they're slow. Anyway, ln y equals 6x is now on the left-hand side. X is ln x. Okay, then erase. Come on. Yeah, I know what it wants. It wants me to restart the program. ln x is on the right-hand side. This is not differentiation yet. We just use log onto the both sides and apply the properties. And now we're going to start differentiating everything. So now implicit differentiation starts. That's why we teach it in the same chapter. Implicit differentiation starts now, because now we don't have y equals. That is the bad part. But the good part, now we don't have the weird function as well. We have product rule, and we know how to deal with that. Left-hand side is always the same. It's 1 over y dy over dx. In some books, you like they always show it. It's always the same because you differentiate ln y all the time. Equals, and whatever is on the right-hand side, just do the product rule. It's always product rule. That's the whole point. From exponential function, we figure out product. So product is better. We know how to deal with that. And it also was not exponential. It was like a weird one. Input to the input. So u times v, again, u in blue, v in black. Derivative of u is 6 because 6x. Copy ln x plus copy 6x. Derivative of ln x is 1 over x. You see, I'm doing it fast because I did it thousands of times. You will be as good as I am when you do it many times. You don't have to do thousands of times, but probably 20 times you'll be as good. It's inevitable. I like this word, inevitable. Now, you are 2 steps away from the answer. You multiply both sides by y because you want to get rid of this 1 over y thing. It's not that you want to get rid of it. You want to isolate dy over dx. That's the whole point. We always want to isolate it. Isolate. So what should we do? Multiply by y both sides. Dy over dx equals 6 ln x plus 6. Actually, x cancel that with x, which is convenient. Multiplied by y. And now I will show. So let me make steps. Step 1. Apply logarithmic functions to both sides. I like numbering steps. Step 2, use properties of a logarithmic function to get rid of the exponent. Step 3, use implicit differentiation to start differentiating everything. Step 4, isolate dy over dx. Multiply by y at the very end, but then you want to change y into whatever we're given. This is the case where y was given. So I don't like rewriting it twice. That saves lots of time if you just put it at the original function over here. That is the answer. That is the answer. What do you think about that? That's logarithmic differentiation. It uses implicit differentiation, so it's not a very new topic, but the first step is new. Let me restart the full program. Now, from here, we can move on to, I think we're missing properties of logs since we're at the log topic anyways.
Can I ask one question?
Yes.
Before we move on? For this one, so we use implicit differentiation and log both sides when we have an x at the base and at the exponent. Okay, just wanted to.
There are 2 cases we teach you when we use it. So it's on my screen. Case 1, input to the input, guys. This weirdos. Like it's not often we see those functions in general in calculus, but in real life applications they are everywhere. So it's nice to know how to do it. So that's when we cannot do just one rule. We have to do logarithm and then do other stuff. And there was another example, log of some complicated formula. We use it there as well. Oh no, when we want to find derivatives, some products and quotients, they say, oh, use logarithm. But most of the time it's for the exponential function. So that's good enough for it.
Okay,
thank you. It's a good question. Good questions, people. Seems good. So what I wanted to remind you is how to work with logs. I know, I always like teaching logs. It's a fun topic. I feel like students overthinking it quite often. But you know, new notation, especially if you missed it from school or your school was like a long time ago. Logs have several properties. And I put like one example there on a test. So you better know it. That's important. We have to make sure you know. This is how it's hard to remember definition. So let me show you how I remember. So you have a to the x, right? That's exponential function. Logarithm's job is to undo exponential function. They are inverse to each other, right? So they're inverse. That's why one was created to undo exponent. It's like x squared is undone with square root, with some kind of suggestions, of course. So this is how I teach the formula. A is the base. So A will stay the base. A will go to the base of log. That's kind of the most important part. What is going to be at the base? Well, A is going to be the base because it was the base in the first place. Now, equals to y. So how to rewrite this into log? X and y change places. That's the whole point. X used to be in the exponent. Then, now x will be isolated. Y used to be isolated. Then y will be as input. Let me make it interesting. So input and output changing places when we use inverse functions. Inverse functions. So x used to be stuck in the exponent and we want to isolate it. Then when we use log, x will be isolated. Y used to be free. Now it will be not free. It will be stuck inside of the log. A is the base, so keep it as a base. That's like the best way I figured out how to teach so people remember it, because it's pretty hard to remember the formula. So the cool property is, of course, you probably remember that ln E is 1, ln of 1 is 0, because ln has E as the base. That's called natural logarithm. But also E to the ln 1. E actually even x. Yeah, like this. E to the ln x, they undo each other. Ln cancels out E. Canceling out is not a proper way of saying it, but that's how usual students remember it. So x stays. And the other way around. Ln of E to the x is also x. Because just like square root and x squared, they undo each other and only x stays. That's the idea. And that's kind of the whole job of the log, is to undo E and to slow down some other functions. So the cool properties are the one we already had, ln or log of x to the y or m to the n, doesn't matter. Y exponent goes down. That's like a really cool thing that it does, that it pushes the exponent down, or you can put it up. That's also pretty cool that you can put it up. And the product and quotient thing. When you have ln of quotient and you have ln of product, then you can write down it as ln of difference. Ln minus ln, or ln plus ln, like so. So just like I mentioned, logarithm function slows down processes. So these three properties are the most important. When logarithm function looks at the exponent, it makes product out of it. When logarithm function looks at the product, it makes sum out of it. And when logarithm function looks at the quotient, it makes difference. So it slows down the processes. If you check how much code it takes in a computer to code quotient versus difference, quotient is faster, but it also takes lots of memory. So difference takes less memory and so on. Slows things down. So can you work with the example like this? It's like a nice example. Where is it? Whatever, then I'll have to just make some up. Okay, example. Can you figure out a square root of ln of x times y over z, I guess, like so. Yeah. You can rewrite this as 1/2 goes down. Parentheses. By 1/2 goes down, I mean this. Oh, no, you cannot do that. That's actually a common mistake, and I just made it myself. So again, ln x of, I'll put it here, not the same as ln x to the y. No, this is not the same. It has to be on, the power has to be on top of the input, then it works. Or else it doesn't work. So I will do some kind of whatever, square root, like so. Yeah, this is good. Can you rewrite it as 3 logarithms? Well, if you see product, that's the sum of logarithms. So it's going to be ln x squared plus ln y. If you see a quotient, that's minus ln squared of z. Because the powers are applied to inputs, you can also now work with those. And the answer will be 2 ln x plus ln y minus 1/2 ln z. That is the answer. From a nasty kind of function with like fraction inside and roots and everything, ln made it look really nice. So that's why it's also used a lot. So again, the square, this 2 came from the square. 1/2 came from the square root. Minus is because square root of z was in the denominator. Plus because it was product. So can you do that? Yeah. This is something I wanted to review too. I think we reviewed all kind of differentiation rule. So after this, we can start reviewing some topics, which is, you remember, what do we have? Related rates, limits, that kind of stuff. Not just limits. I mean, like there are limits at the very end. Let me check. Watch by yourself the equation of a tangent line video. I have that. That is very important. We always put equation of a tangent line on the exam 2, exam 3, and the final exam. So the earlier you learn it, the better. And equation of a tangent line goes to calculus 2 and calculus 3. So you have to know it.
This was just a simplification problem, right? Not a differentiation.
Yeah, let us just rewrite it basically. Let's do, okay, I see related rates, linear approximation, and then exponential function and log is inverse to each other. Oh, you guys know second derivative, right? If you're asked to find second derivative, you just repeat the whole process. There's no special formula for upper level derivatives. So if from any of this you're asked to find y prime prime, you just differentiate everything one more time. And 1 prime prime prime, differentiate everything one more time. So upper level derivatives, I have video on that too. You just unfortunately have to move on with it. You just have to keep going until they believe it's done. Oh, nice. We reviewed a lot of stuff. Actually, only several topics left to review. So let's do related rates. Check this out. So basically, differentiation review is over. We now start reviewing topics which are applications of differentiation. Let me just call them applications. Applications, and not necessarily real life applications. Differentiation is everywhere. So in some point, we're going to teach you, the blood pressure in your body, that's derivative 2, and implicit differentiation is there too. It's very interesting. Magnetic fields, we do black holes right now in calculus 3. Lots of derivatives everywhere. So it's pretty cool, very interesting, especially in upper dimensions, in high dimensions. So remember those like classical problem for related rates, Okay, I'm getting sleepy. What is that? Told you I'm not an evening teacher. Related rates. I like to teach like 8 in the morning. So related rates, you did not like this problem with the shadow and like walking people in the boat, but actually I have videos on all of this. I remember I saw them all. The classical one is with a balloon. The balloon is increasing, or the classical one is the oil spill, because then it's just a circle. So if the balloon is being inhaled, whatever, increased, right? We give you the volume formula for the balloon, which you're supposed to know if you are in engineering and physics major. Actually, all STEM people should know this formula, but it's fine if you don't. Just look at it. I mean, on the test, we give you guys formulas. So here's the formula for the volume of the balloon, right? And then the oil spill is actually pretty cool. You can calculate how far the oil will get, for example, to Florida, right? So people would evacuate animals. It happened before the huge oil spill around Florida. So math and specifically related rates problems are calculating how fast the oil spill gets to the shore and how much time you have to evacuate people and animals. So you have this formula, V equal, I would just put it down. The idea is to differentiate everything you see. That's why it comes right after implicit differentiation formula chapter. Implicit differentiation. So you differentiate everything you see, keeping in mind that both volume and radius are functions. How do I know? Because I read the problem. The problem says, well, the radius of a balloon is increasing and the volume of the balloon is increasing. Okay, the phrase increasing, decreasing, that's the synonym of the phrase changing. Changing. So instantaneous rate of change. You know, changing is also a synonym of derivative. How fast something is changing, that's derivative. So if it's increasing or decreasing, you know what to do. You take derivative. So we're taking derivative of this raising formula, keeping in mind that V is the function of time. The volume of the balloon becomes bigger with time. But also R is a function of time. The radius of the balloon also is getting bigger. Well, because it's increasing, right? So they are related via third variable t. That's why we call it related rates. And usually everything is related through time, so it makes sense. In calculus 2, we will have higher dimensions. They will be related through gravity and time and the color, for example, and the density and so on. So dv over dt equals 4/3 pi r cubed. You first differentiated the way you know it's 3r squared. But then you remember it's also a complicated function that depends on t. So it becomes dr over dt. Okay, this is the first step. You differentiate everything, keeping in mind that we have two related rates, and they usually give it to you in the text. You have to read how it's written. And then they give you one rate and they ask you to find another rate. That's it. So don't overthink this. They usually give you one and then ask you to find another one. If, and now you have to read carefully, what is given. For example, if the volume of the balloon, okay, if the volume is changing, and then they have, when you see the word, there's keywords I like to teach, changing or increasing at the rate, right? That is also synonym of derivative. That means they're talking about derivative. And then you look at the word before or after the derivative of what, and they're saying the volume or they're saying the radius. That's how you know. Is changing at a rate. And they give you a rate, say 1,000 centimeters per minute. If you see per, that's derivative. So that's one of the keywords. Let me go back and add it here. If you see per, which is slash rate, right? Those are all simple signs of derivative. So when you're driving 50 miles per hour, that's speed, and speed is derivative of distance. That's how you know it's per or rate of change. So it's changing or increasing, decreasing at the given rate. Find the other rate, the rate of change or increase of the radius. So again, one is given, the other one is not. So in this case, your job is to carefully read it and then add. No, let's not do add. When radius is like what? 7 centimeters. So this is how you read it. I'll change the color now to like show you how, especially if you're not an English speaker as a first language. So ESL students, English as a second language students, I always feel compassionate to them because it's hard. Like, why so much English when you're trying to learn derivatives? American system of education have lots of wordy problems. It's very hard to be immigrant in the math classes in the United States. So high respect to everyone. Hispanic students, amazing. You're doing amazing. So just keep pushing, keep pushing. So I like to teach my Hispanic students, in general, international students, anyone who learn English, right, in the same time with math. You look for the keywords. So I'm seeing the keyword changing. I'm like, okay, something is changing. That's derivative. That is some kind of derivative. Whatever. Like Julia says, changing rate is a synonym of derivative and per or slash. Okay, so that this number is a derivative. Derivative of what? You go back a little bit and see that word. It says volume. Oh, it's V prime. So V prime is given. So I'll write down, instead of derivative, I'll write down dV over dt equals 1000. That's how you know, because you have like two different numbers. Which one is what? So now I know that is given. Well, if this is given, there's only one rate left, dr dt, then it's not given. And that's one we need to find. Okay, now I'm getting where it's all going. But then there's also number 7. How do we know that's not a derivative? Okay, let's read about it. Let me change the code. Find the rate of change of the radius. Okay, that's the one I just mentioned. That's dr dt is not given, and they want us to find when radius is 7. See, this interesting. Radius is 7. There's no per, there's no slash, and there's no changing. That means that is a fixed value. R is 7. Now you know what to do. You plug all values, but you only do it after you differentiate it, which I already did. After differentiation. Oh, that's a long one. Okay, so you only do it after. If you plug 7 too early, it will not work. So we have dv over dt. Let me simplify it, I guess. 3 and 3 and 1/3 cancels out. It becomes 4 pi r squared dr dt. And I'm taking a pencil and I write down all the numbers. R is 7. Left-hand side is given as 1000. Right-hand side is the one we need to find. Nice. So now I know how to solve this equation. I just need to solve it. Solve for right-hand side. To solve for right-hand side, you just divide by everything that is attached to it. 4 pi 7 squared. Maybe you first rewrite it. So it's 1000 equals 4 pi 7 squared dr dt. Divide by 4 pi 7 squared, which is 49, by the way. 4 pi 7 squared. And you got the answer. Dr dt is 1000 over 4 pi 7 squared, which like totally should have simplified, but I don't want. Okay, there was also like a small mistake. I just realized it while writing. I wonder if anyone noticed there was like a weird mistake. But calculation wise, it's good. So I will mention the mistake in a second. Related rates. Step 1, read the problem. Step 2, differentiate everything you see. kind of keeping in mind what is the variable and what is not a variable. Step 3, write down what is given. dv over dt was given. R was given. I like to make a table like this. And then the R over dt is not given. That's what we want to find. Plug it in. Yeah, you don't have to simplify it for the test. So it doesn't matter. So the mistake was, this is centimeters per, what was it, meter? Centimeters per minute. Not this one. Do you know what this one is? It's volume. Volume cannot go in centimeters per minute. It should be centimeters cubed. And it doesn't matter for your exam, but in general, if you physics and engineering major, you will be asked this many times. Don't forget the units. Units have to be perfect. For math major, we don't really care. And computer scientists also will not care too much. That's related rates problem. I have videos about the second case as well, so you can definitely watch that. Very nice. Let me know if you have questions. Then let's move on to the back to exponential function and some limits stuff. So I want to talk about e to the x versus log and ln x. So we need you to know the graphs. That's important. That's why I posted some cool animation in one of my announcements, how those functions work. Check it out. E to the x is like a shooting rocket. It goes very slow first until it hits 1. Zoned out for a second. At 0, it is 1. And then it shoots up like a rocket. So that's why in the movies they always say, oh no, zombie apocalypse, the disease spreads exponential, because it means fast. They just know it means fast. They don't really know what it means, but they like it. Sounds professional. Exponential growth means fast. That is why logarithm growth is slow. It's still growing, but it's slow. To draw the inverse function, you draw a mirror first. A mirror, y equals x. That makes sense because inverse functions reverse input and output. So y equals x is literally what it's doing. And then you draw a mirror. Everything copied like so. That is ln x, basically. So ln at 0 does not exist, but ln is 0 at 1. So that's when they are symmetrical. Okay, my exponentials kind of ugly, but I can redo that. Like so. So exponential was slow, then it became fast. Logarithm is the other way around. It's first very fast. It grows fast at first for fractions, for numbers between 0 and 1. But then it becomes slow. It's still increasing, but it goes up slowly. So that's a pretty cool idea. Why I'm telling you this? Because you had questions in your homework asking about the limit. So for example, what is exponential function doing e to the x? As x approaches infinity, guess what? It is infinity. And logarithm function, ln x, as x goes to infinity, is also infinity. Both of them are growing forever. It's just one is slow and the other one is fast. The difference is what's happening on the other side of infinity. The exponential function, what is happening when x goes to minus infinity? You're like, I don't know. So there are 3 ways I can explain it to you. Way number 1 from the graph. If you look at the very left, see, it keeps shrinking to 0. So on the very left, e to the x becomes very small, it shrinks to 0. Okay, what if you don't remember the graph, which is usually a common thing, which is fine. Then 2 other ways to explain it. E to the x, as x becomes negative and big. You can imagine it. You can always rewrite it as 1 over e to the minus x. Let's do like so. That's a very popular trick to do. 1 over e to the minus x. Well, now minus cancels minus. And we have 1 over plus infinity. And if you remember limits from the previous exam, and I also have videos, 1 over infinity is 0. This is how I like teaching it. When you're dividing by the biggest numbers you know, that's infinity, right? You get the smallest number you know, that's 0. That makes sense. Denominator explodes to infinity, and the whole fraction shrinks to 0. But did you get it why denominator goes to infinity? Because when x goes to minus infinity, minus minus gives you plus infinity. And e at the plus infinity is infinity. We just kind of agreed on that at the first step. So that's a second way of seeing it. And the third way of seeing it is just using a damn calculator. If e to the minus infinity, what is that? We just grab a calculator and plug some kind of like 10,000, but don't forget minus. E to the minus 10,000 or more million, right? 3, like so. Is it a big number or is it a small number? Yeah, it is small. It will be 0.000, blah, blah, blah. So that's how you know. You can also use calculator just to check yourself. Now, what is happening with logarithmic function at minus infinity? It's not there. It doesn't exist beyond the wall 0. This wall, x equals 0, is a vertical asymptote, VA, for logarithmic function. That is why you will never have this question. It's not going to the left forever. It stuck at the wall. That's why instead, the question will be, what does it do at 0? That is also not correct because at 0, but not from the left and right at the same time. It's only approaching it from the right. Plus means from the right. It's like if you say it out loud in English, it makes sense. From the right. Because green color function, which is log, is always only on the right. Then grab your pencil, put down, and see visually where it's going. Oh, it's going down forever, so it's minus infinity. Again, you could just use calculator. Just plug ln of small number close to 0 but positive, 0.00007, and see, is it a big number? Is it a small number? Well, it will be big and negative. So that's minus infinity. Big, but negative. So minus big. That's important. So make sure you know how to do that. Example. Let me see chat first.
I had a question about the limit of ln x as it's approaching infinity. Why is it
plus infinity, right?
Yeah.
Plus infinity
1.
Yeah, that's a good question. So you put, it's actually very not obvious at all. When you put a pencil, x is keep going to the right forever. So that's to the right, x. Then you put a pencil to draw log. It will go like this, and it actually will be slowly growing. It never stops growing. So it doesn't have horizontal asymptote as 1. That means it goes to infinity. Yeah, that makes sense? In general, you can see it this way. E to the x is going forever, and it's also increasing. And it's always decreasing because log recreates e to the x, but using a mirror, it's keep changing as well. But it goes to minus infinity and plus infinity, like so. Yeah. I wanted to check this example. For example, so that's and we're going to do L'Hopital rule right after this. It's very natural to go to L'Hopital rule right now. Yeah, so I'm talking about this example. Check it out. Limit as x approaching plus infinity and limit as x approaches minus infinity of the 9 over 5x minus 7. 9 over 5x minus 7. Like so. Why so uncle? 5x minus 7. Good. Equals. Okay. At infinity, exponential function grows to infinity. You can check. You can plug 5 to 100. Always plug some kind of big number. So 5 to 100, 1000. That's going to be a huge number. So at infinity, exponential function grows to infinity. So you have 9 divided by infinity minus 7. Guess what? Infinities do not care about constants. Constants are too lame in the eyes of infinities. Infinity is like an explosion. It doesn't care for small things like not moving objects. And constant is not moving because the constant. So it ends up to be 9 over infinity. Dividing by the biggest numbers, you know, gives you the smallest number, you know. This notation over here in yellow is not professional. So other professors will tell you, oh, you're not supposed to write this. But this is very visual. I like writing it down. We're dividing by the biggest numbers. We know that's infinity. So we're getting the smallest number, you know, that's 0. That makes sense. However, when we go to minus infinity, everything changes. Now you have to remember, what does this function do, 5 to the x, at minus infinity? And I gave you 3 different ways to remember it. Way number 1, from the graph, the tail shrinks to 0 on the left. And on the left is where x goes to minus infinity. So y, that's a height, right? Y is height, shrinks to 0. Either you remember that, or just plug in the calculator. Check this out. 5 to the minus 1000. If you plug it in calculator, trust me, that's going to be a very small number, right? So now you know that the thing is in the red, shrinks to 0. So the answer will be 9 over 0 minus 7, which is minus 9 over 7. And that is the answer. Does that make sense? So that's 2 different answers. On the right, this function shrinks to 0. On the left, this function shrinks to minus 9 over 7. Very cool. And finally, we're getting to L'Hopital's rule. That's students' favorite rule. If you are behind on the recent homework, well, you should do it as soon as possible, right? Actually, I have video solutions for almost all of your homework problems for this chapter 3.7. Because it was fun to do it, and I just did all of it. It's called the L'Hopital rule. H is silent. H and S is silent. L'Hopital rule. L'Hopital's rules is fun. It basically says if you have a limit with a function u over v, let's not do quotient rule notation, f over g, and you have 2 cases, infinity over infinity and 0 over 0, then instead of working with f and g, I should just bet location. Only for those 2 cases, instead of working with f and g, just work with derivatives, f prime, g prime. And it's not a quotient rule here. You differentiate the top and the bottom separately. How cool is that? So, for example, let me figure out some kind of cool example. Yeah, I figured out a cool example. That's not all about L'Hopital rule, but that's the main one, just like the most cool one. Limit, we have e to the x minus 1 over x. X goes to 0. So we're going back to the limits notation. This chapter should be in the chapter of limits, but we did not learn derivatives there then. So now it's kind of rolling back to the limits. L'Hopital's rule tells you, instead of working with the original function, sometimes it is better to work with derivatives. So let's see what's happening. Well, you know, step 1, plug in. Maybe we are overthinking and everything is easy. E to the 0 minus 1 over 0. Okay, definitely have division by 0. That is not good. And I have 1 minus 1 at the top. So it is 0 over 0 case. That's called case. 0 over 0 or infinity over infinity case. Since and only because of those two cases, you cannot use it for any other case. Since we have 0 over 0 case, so we can use L'Hopital's rule. Usually people put it in a circle. Actually, that's not international notation, but I like it. And that means we're working with derivatives now. You put equal sign, so instead of, it's professional to do like this. Let me show you. L'Hopital's rule is used here because right now you will write down something so weird, you will not remember it later. And that's why making a note, what did you do, is smart. And you did it because it was 0 over 0 case. I'm taking derivative of the top and of the bottom separately. So it's very simple. You don't have to do quotient rule. E to the x gives you e to the x. Minus 1 gives you 0. Derivative of x is 1. So the whole idea of L'Hopital rule is, instead of working with original function, let's work with derivatives. It says that in some cases, derivatives behave as original functions around 0. So why not to work with them instead? Well, do you know the answer now? Yes, we do. You plug 0 again, it will be e to the 0, which is 1. Boom, done. So that was super simple. That's why L'Hopital rule is so pleasant. Students like it. Usually, you don't have to remember too many things here. You just need to know, take derivative here, take derivative there, move on. You're amazing. Just don't overthink this too much. But you do know that there were some cases. Yeah, there were other cases. You should learn them. I have video on each case. For example, what if it's not even a quotient? Then what? So, well, there's no good example. Let's lame. Let me create one example. Example 1, example 2. For example, if you can, just create a quotient. So, a limit x goes to infinity. Let me create a nice example, and it's going to be x to the 7.3. Why not? Let's do 7.3 times e to the minus x to the 5. I guess. I don't know. Let's see how it goes. So this is a product, but we were told that it's only have to be quotient. So sometimes what people do, they create a quotient out of product. So why not? You can do that. So how would you do that? I'll write down the limit. X goes to infinity. X 7 raised to the 7.3 stays, and e to the x to the 5 with a positive exponent goes down. So what I did, I basically wrote e minus x to the 5 as 1 over e x to the 5. Because you can always move terms to the top or to the bottom of the fraction by changing the exponent sign. So now we do have a quotient. Let's see if it's 0 over 0 or infinity over infinity. At infinity, we just reviewed exponential function indeed is infinity. X to the stuff at infinity is also infinity. So it is infinity over infinity case. Since in an infinity over infinity case, we can use L'Hopital's rule. Yeah, the example was not very brilliant. It's fine. I guess I can tell you that you should use it many times here, but whatever. So that means, people should put it in a circle. It means goes to infinity. I'm differentiating the top separately. 7.3 goes down. X 7.3 minus 1 becomes 6.3. E to the x to the 5. What is that? Well, that's chain rule, right? Copy e to the x to the 5 times derivative of the exponent. X to the 5 gives you 5x to the 4. And now you can simplify stuff. Look at that. Look at that. So I can simplify exponents, for example. And do it again, and it will work second time. So you can do L'Hopital rule as many times as needed. Limit x goes to infinity. I have 7.3 at the top x is raised to 6.3 minus 4, that's 2.3, divided by 5, e to the x to the 5. And you check, and it's again infinity over infinity. So you do it twice. Some examples even need 3 times, 4 times. You do L'Hopital rule again. And this time it will be enough. You will see why. Let me do it here. Limit x goes to infinity. The denominator will be 5 times e to the x to the 5 times 5x to the 4 one more time. Last time it got simplified, remember? The numerator will be 7.3 times 2.3. See, I don't even care to simplify. Who cares? X to the 2.3 minus 1 gives you 1.3 power rule. And finally, the x simplifies so nicely that the numerator ends up to be a constant. 7.3 times 2.3. I don't even care what constant that is because the whole answer will be 0 anyways. X goes to infinity. The most important is where the functions are located at infinity. Denominator is 5 e to the x to the 5 times 5 x to what? 4 minus 1.3, which is 2.7. I can explain you that in a second. The whole goal is numerator have no functions. Those are constants. So you have exactly the same case as we had here. This one. 9 over infinity gives you 0. Constant over infinity means constant divided by the biggest number you know. That gives you the smallest number you know. E, that's 0. Because e to the x to the 5 goes to infinity. X to the 2.7 goes to infinity. At infinity, constants do not matter. They stay. They don't move. So you have division by infinity. That gives you 0. Note. What I did was x to the m over x to the n is x to the m minus n. The two properties I want to show. Top minus the bottom. But x to the m raised to the n is a product of exponents. So that's what I did. So we had 1.3 and 4. 1.3 minus 4 is minus 2.7. And then I just kept it at the denominator. So the sign was plus. Oh, that's what I wanted to show. What do you think about that? So we did this. We actually did lots of stuff that will help your homework as well. We did arctangents, logarithmic differentiation. Let me do one more derivative. And then I will do approximation, the stupid linear approximation. I never liked it because I think they only teach it in the American system. But, you know, it's very practical for engineers to know. I guess everyone should know linear approximation. But let me ask you one more function. Do you know how to differentiate y equals, for example? I forgot what number it was. Example 57, for example. I don't know. 30 sine of, well, ln of x squared. Oh, I wanted to ask you that. Can you differentiate that? Let's chain rule twice again. So first I'm finding which function is outside. The function outside is sine. 30 cosine, derivative of sine is cosine. Copy everything inside because you have no right to touch it yet. It's like a Russian doll, it's still locked. Now, when you do times, this is when you unlock it. That's chain rule. Chain says, now I'm allowing you to look one level inside. One level inside, I see log 12, actually, 12 times log of stuff. Well, I know what's derivative of 12 log of stuff. It's going to be 12 times 1 over that stuff. So 12 over x squared. Let me put it in different color. X squared, 1 over that stuff times chain rule happens one more time, and it says, well, I see one more stuff inside. Look at x squared inside, not 1 over x squared. Be careful with that. So you do times derivative of x squared, which is 2x. So can you do this by yourself? You know, like tomorrow, can you don't look at my solution? When you play my videos, it's actually very nice. You play and you pause over here. You solve it by yourself. You figure out what's the answer. And then click play and see how I do. And then, you know, if you did it well, good job, move on. If you didn't, you get frustrated, but that's how you learn. And you just redo it. And that's how you learn the things. Chain rule twice. Can you do that? And the last thing left to do, exactly 5 minutes left. Wow, so professional, just exactly 2 hours. Is that logarithmic? No, we did that already. Approximation, linear approximation. The idea is pretty beautiful, to be honest. It's just annoying when it comes to exam. But if you ever watched the Hidden Figures movie, which you should, they actually do mention Euler's method there, and it is linear approximation. Derivative. I think it's here. Linear approximation, inverse, implicit, logarithmic applications. Yeah, check it out. How cool is that? I have lots of cool animations, but the idea is functions have derivatives. Okay, we kind of got that. We're struggling with that. Derivatives gives you a tangent line, right? So tangent line is this, and we ask you on the test. There's a problem asking you to find the equation of a tangent line. Tangent line has a formula y minus y0 equals mx minus x0. That's the equation of the line going through a point with a given slope, and also mx plus b, right? So both are good. Use any you like to find the equation of a tangent line. Step 1, find derivative, plug the point, get the slope. Step 2, plug the points, you got the equation. My point is, linear approximation says if you zoom in a lot, so zoom in, see, it gets, don't do that. It gets closer to the line. Zoom in even more. At some point, the dots between the black function and the red line are the same, or at least they're very close to each other. Look how close they are. Of course, I don't want to talk about something like here. Like this one is not close to this one. That's stupid. We don't talk about that. We talk about around P. Around P, if you zoom in a lot, and that's what this picture is doing, the points become more or less the same. So why even bother working with a regional function, which can be like arctangent of logarithm and whatever? If you can take derivative, if you can find slope and use that instead. So that's what they do. They work instead with this point and this point and this point, instead of the points on the black curve, which was the original one. And then they find the difference. That's called error, right? That makes sense because it's going to have some error. And if the error is small, and usually small is like 0.00001. If the error is like 0.001, they say it's fine. So the idea is pretty awesome. And it's very applied. Like it has lots of cool applications. So again, in Hidden Figures movie, they mentioned it. It was very exciting to watch as a mathematician. Here it is. Zooming in, zooming in, zooming in, zooming in. At some point, if it's that close to the tangent line, why not work with tangent line? Lines are good. Other functions are annoying. Everything is good except line. Everything is not good except lines. Lines are amazing. They're linear. They're predictable. Anyway, that's just a lot of blah, blah. But actually, yeah, I'm talking about Hidden Figures here. I usually mention that. They used Euler's method to make sure that the shuttle is landing on water, not on land, for obvious reasons. Your job is to remember the formula. The formula is I mean, in general, it is still y equals y sub 0 plus m x minus x sub 0. That's the same thing. We're just kind of renaming it to be more cool. We're saying that m is derivative at a, that's slope, that makes sense. X minus a, that makes sense. F at a, that's more y. So all of those things are the same. And the left-hand side, let's call it L, and L will be linear approximation. Instead of original function y, we will use with L, and we claim they're close enough. And the error is exact minus approximate. So let's call it the error. So, and they gave you those weird examples at home. So one of that is on the exam. That's not a secret. We take examples from your homework and I just put it there. So in general, you need to remember that just a formula basically. Y equals original function at the point we give you, that's called A, plus derivative at the point we give you times x minus that point. If you remember this formula, you can do stuff. So like several weird examples there. For example, there was like a square root of x at x equals 49. Guess what's going to happen? That is y, right? That's y equals square root of x. Well, y equals, it's like not very anything new. Square root of x, that is f, right? A is 49 plus derivative of f. Let me call it f for you. F is square root of x. That is given. A is given. The square root of 49 plus derivative of square root at 49. Well, what is derivative of square root? 1/2 goes down, x to the minus 1/2. And x is 49. So keep plugging. It says here, plug 49. Times x, don't plug that x is variable here, minus 49. Okay, I got this. Looks super ugly. We always want to rewrite it in the form mx plus b. How to do that? Simplify everything and move it around. Which means, let's simplify. Y equals square root of 49 is 7 plus 1/2. What is 49 to the minus 1/2? Remember, you can rewrite it as 1/49 to the 1/2. And 1/2 is a square, so it's 1/7. X minus 49. Is it mx plus b form? No. So rewrite as well and continue. Y equals 7 plus 1/14x minus 49 over 2, well, over 14. I just want to simplify 14. Is it in the form? No. Keep writing. 1/14x. Okay, that is mx. I like that. That is m. Nice. We found m. And what is b? Well, it's a simplified thing, basically. So it is fractions. Plus 7 minus 7/2. Oh, that's not too bad. 14 minus 7. I think it's 7/2. That is B. See, that's what they're talking about. That's what they're talking about. And then they say, well, use that to find something else. And you just plug it in. Either use your calculator or you plug it in. So linear approximation. I have lots of videos on that too. So kind of, I feel not too bad that we only can cover one problem before I start coughing a lot. Yeah, what do you think about that? questions, ideas, suggestions? Overheating computer. Yeah, in my classes, I always show lots of cool animations. So that's why I have cool pictures here. So sine behaves like line y equals x around 0. So that's a very common thing to do, to use approximation. Differentials, you should review differentials, but they are not very bad though. Differentials are this kind of thing. I cannot tell you if they're on the test or not, so you should review it. But this is, it's a dumb topic, honestly. It's kind of like that. Delta, so dy over dx, if I read it this way, equals, I don't know, 75. Do you know what they did? So there's a whole anecdote about that. We keep teaching, can you stop? Yeah, we keep teaching that this is not a fraction. And then because it's not, like it's dy dx, it's not a fraction. And then you know what they do? They multiply by dx. So dy end up to be 75 times dx. And it's like kind of super dumb. Basically, it doesn't hold lots of new information until you go to numerical analysis. But in general, it means small change in x and gives you some kind of small change in y. So that is important. Will you post the recording? Yeah, I'm gonna post the recording when it's gonna be prepared. It takes, I think, 1 hour or 2 hours to create a recording of 2 hours long. So the question is also about the multiple choice test. I always make announcements saying they will be both. So in case there's both, then I don't feel guilty I didn't mention it. Or some of them are randomly taking problems. So that's why I cannot predict. But most of them are not multiple choice at all. Because we need to see how you write down derivatives. That is a pretty writing exam. Like you have to write down stuff the way we did at the very beginning, with chain rule and everything. But yeah, I can see how it was confusing because I mentioned it in the announcement. Because some of them do have, and I don't want to make every time new announcement. So I said and or. Yeah. Yeah, good job, people. Very good questions. Any last question before let's do this shutting down? Good job. Survived my poor old template. Yeah, please submit a scratch paper and I can share with you those notes. I just did, not a problem at all. So why wasn't it 7 plus? Did I make a mistake? Let's see. There's a question. 7 plus 1/2.
Yeah, it's just on this y equals 7 plus 1 over 14x minus 49 over 14. Isn't that 49 over
49 over 14
plus the 7? Wouldn't that get did you take
Yeah. I think I did 7 minus 49 over 14. That is 7 minus 7 over 2. 7 times 49, yes. And then I did 14 minus 7. 7, 7, I think so, right? Oh,
and then the 7, that's right on the beginning. That's 7 plus.
Oh, that's
1.
the one, yes. Yeah, square root of 49. That's the 7.
Oh, okay.
Right? Or am I wrong? So this came here, 1/2, 1 over 7, because it's square root of 49 and 1 over. Hope it. Yeah. And then I just tried to add up.
Minus 3 plus 7.
You are disconnecting, or I am disconnecting. Okay, yeah, I think you got disconnected. Maybe you can type it in, then I can see. And there's a question typed in if we reviewed the inverses of derivative. We reviewed arcsine, we reviewed derivative of arctangent, arcsine, arcsecant. Oh, the final step. 14x. 14x goes in front because it's mx. And then I have 7 minus 49 over 14. I simplify that to be 7 over 2. That is 14 over 2 minus 7 over 2. That is 7 over 2. I think so, right? Good job, people. Yeah, good job for coming. That's already very impressive that people want to know stuff. And especially it's late in some places, some states. So I think I'm happy my voice handled it too. Now I really want to go and cough a lot though and drink some tea. But I will post my notes for you. I think people like having notes. Some people are visual learners, so they want to see stuff. So I'll post the notes for you. And this video is coming tonight. It will take 2 hours to be created. Thank you. I'm recovering slowly. The fever was horrible, and I only a couple days have no fever, so it's very getting successful. Getting there. Thank you.
Thank you, Professor.
Thank you for coming. Have a good night and good luck on the test. You'll do good. I hope people do A+.
Thank you so much, Professor.
Sure. Have a good night. Stop. And